Hello Internet, this is JF, and this is Introduction to Programming in ATS. This is Video 6 and Chapter 6, Effectful Programming Features. This is also the first chapter of the second book. The first book was all about the functional core of ATS, and this were a different language that could have actually been the entire book. It could have been just ended at Chapter 5 and said, okay, that's it. Now I know the language. If you want to actually do stuff, pick up a reference or read the documentation for the standard library, and that's it. You can go out and treat it like it's any kind of ML. But in fact, there's a lot more. There's in fact several other books. So let's get right into it. Effectful programming features are those that can generate effects at runtime. But what is an effect? So he's going to gradually introduce various kinds of effect. So even though this is effectful programming features, we're not going to talk about all of them right now. So in sequential programming, an expression is effectless. There are no effects. If there exists a value such that the expression and the value cannot be distinguished as far as evaluation is concerned. For example, the expression 1 plus 2 is effectless, as you can't distinguish it from the value 3. If you have somewhere in your program a factorial 5, you can just go and replace that with 120, and if that doesn't change anything about the program, then factorial 5 was effectless. What you'd expect. You'd expect it to be a pure and total function. All right, so an effectless expression is said to be pure. On the other hand, an effectful expression is one that can be distinguished from any given values. For example, print hello is effectful as that the evaluation results in an observable behavior. Something happens when you print hello. It's very weird. And that thing that happens when you print hello is distinguishes the expression from any values. Like, you can't just go into a program and take out print hello and then type some kind of value and have not an expression but actual a terminal value and have that result in the same program. No, they're totally different now because you're no longer printing hello. So so print hello is said to have, I think it's a certain IO effect. So the way I was thinking of effects prior to reading this paragraph a little bit more carefully is that you have an effect non-termination, and that's one effect, and all of your categories are effect of there's just one value in that category. So if you were to say I would expect this to read print hello has the IO effect, so there's one effect and just print stuff. But apparently if you print hello, printing hello is an IO effect. And if you print by, that is a different IO effect. So there are multiple IO effects. So if the evaluation of an expression never terminates, then the expression is also effectful because you can distinguish it appearing in a program. For example, we have this over here. We have an infinite loop, and we have an assignment. We have this expression right here in the program. So let's run that. Another program does nothing forever. And that's commented out. Yeah. Now, clearly something has changed, but that means there's an effect in place because the program shouldn't change if I just take out a loop and replace it with some value that's equivalent to the loop. Now, there's no value I can put in here. There's no magical non-termination value. There's nothing like that in ATS. I can only have an expression with an effect that causes the program to not terminate. All right, and then he goes into that. So this chapter is going to cover exceptional control flow, so exceptions, persistent memory storage, so references and arrays, and simple I/O in this chapter. All right, so exceptions. The exception mechanism provides an efficient means for reporting a special condition encountered during a program evaluation. Okay, so you could have optional types, but then you have to ferry those throughout your program or throughout whatever's using them. But you can just have an exception instead, and that just cuts right through it. As we have an example down here, div exception. So previously we had div opt, returned either sum and then the value of the result of the division, or it returned none. But then of course the caller of div opt has to check that, and you have to do other things. With div exception, you just call div exception where you want to have division. You either get division or you get an exception. So it just protects you from division by 0. So the type EXN is predefined in ATS. So there's a type called EXN. You can see it right here. I take a value of x and I assign this exception to it. And it's an extensible data type that you can create new constructors for. So normally if you have a data type, if you create a data type, you have your constructors right there, and that's it. You can't extend it later on. That would be absurd. At least it wouldn't be a data type, so it would be some other feature, like something object-oriented probably. But exceptions are different. You can create exceptions throughout your program. So you can just create constructors whenever you want them. All right, so it talks a little bit about that. So a raise expression is of the form $raise expression for some expression exp. So clearly, if the evaluation of exp returns a value, then the evaluation of raise x leads to a raised exception. So even though you have fatal error, which returns a value that's of type exn, you don't actually need that. I just had to add it for some reason. So this is an expression and returns the value of exn. But this is also an expression. It's called a raise expression, but it doesn't return a value. And for some reason, oh, what? That's still there. I'm surprised it didn't complain. Uncaught exception at runtime. So, okay. Well, that's weird. Let me say val x, val int. What if I don't have this anymore? Okay. All right, earlier in a previous take of this video, like raise expressions by themselves, like without some kind of like, for example, a case around them, I was getting like a weird error. And I thought, oh yeah, I guess you just can't do that. But apparently no, they really are normal expressions without limitation. So they're not some kind of degenerate expression you can't use like in this case. So yeah, val x int, and you can assign. So I'm trying to bind an expression to a value or to a variable. So this expression has some kind of value, and you can see, well, clearly it has the value of int because that passes type checking. So yeah, so a raise expression can have any kind of value. This has to be an exn. All right, so a raise expression can be captured. If it's not captured, then it bubbles up and aborts the program. So in ATS, a try expression, or a try with expression, is of this form. You have try, and then you have a single expression. Is that really true? Apparently, that's not true. This isn't EXP. This is a sequence expression. You just get it for free. It's like let in, try with, or let in end. So yeah, so you can have try and then as many expressions as you want, and then a with, and then you can have a CL sec. It says here, which is what is it? Clauses, a sequence of clauses. So pattern matching. Yeah, a sequence of matching clauses. So when evaluating such a try expression, we first evaluate exp. So we evaluate all this together. And if it leads to a value, so if the evaluation succeeds, there's no exception effects happening, then you just return that value. But if it raises an exception, then we try and match it. And if there is a match, then the raised exception is caught, and we continue to evaluate the body. So if this matches, then the value is void over here. If there's no match, then the raised exception is uncaught, and then it'll bubble up, and then presumably it'll either kill the program or another try with expression will catch it. It also says that the with part, this whole part of the expression, is called the exception handler. Okay, so this is an example of using exceptions. So we have a bunch of list prod functions. Go away. And the first one, it just multiplies, so it takes a list event. So let's say you have a list of 100 integers, and you run this against it. It'll give you the product of that list. So it'll take every integer and multiply them by each other, and then give you the final result. So, if you have 1, 2, 3, and 5 in a list, and you multiply them all together, you get 1 times 2 times 3 times 4 times 5, so 120. Then if you have, here's another function. This is exactly the same thing, but it has an optimization. It says, okay, while you're going through the list and multiplying stuff together, not actually multiplying stuff together, while you're going through the list and setting up multiplications, it'll be evaluated after you return. So when you do that, if you find a 0, then just return 0. So if you have a list of 10,000 integers, and then the second integer is 0, then this function will only go too deep into that list. Okay, so here's the first one. So let's say 5 times, the second one, the second one's 5, 5 times 5 times, 0? Okay, it's 0. It stops there. It doesn't actually stop there completely, though. It still does the multiplication of 5 and 5 after this returns. So here's list prod 3 with an additional optimization. This one says if you find a 0, don't just return 0 and then do like let's say you had a list of 10,000 integers, and then the very last integer in the list is 0. So okay, well now that you know it's 0, now that you know that the result of the thing your purpose in life is to multiply numbers together in lists, and you know the ultimate answer is going to be 0. You know that as soon as you see this 0. But even so, even though you know that, go and do all this busy work. Go multiply these other like 10,000 minus 1 numbers together. It's like, well, let's not do that. Instead of just returning 0 and doing all that busy work, let's raise an exception that'll cut through all that multiplication and just return 0. So that's what this try with expression says. It says, okay, do that thing we were talking about. So multiply all those numbers together. But if you raise this exception, then return 0. So that's an extremely optimal form of list multiplication. All right, so these could be defined tail recursively, but then you'd have to do the multiplication. Like if you had an accumulator, then you reach the end of the list, and you've already done the multiplication, and now you finally know it's 0. So this is a case where a non-tail recursive function could conceivably be more efficient because you know you don't have to do all that multiplication. All right, and then he talks about that. So one thing to point out is that EXN is a linear type, which I think is odd because I guess there's something weird going on here. Oh, no. This isn't a linear type. But when it's raised, it becomes a linear type? No. Rather, this right here is a constructor. So it's a function that takes no arguments and returns... that's really weird. Anyway, when you raise exceptions, they're linear, and then this tilde matches deconstructs the linear value. So deconstructs it terminates it, which in the case of linear objects with allocated memory, it also frees that memory. But the important thing is that it's a termination of a linear value. Okay. So exceptions are not a programming feature that is easy to master, and misusing exceptions is abundant in practice. So be careful. And here is a full example of brawn trees, which you can go through yourself. I'm just going to go and skip the whole thing. So references. So a reference is just a singleton array. So you have an array of one element. If you have a type T, a reference for that type T has the type ref of T. So Alex, use X again. We're going to call this a ref event. And this has, okay, now we've got the type. We've got how do we actually create these? Okay, it's a template. All right. And that works fine. So the following simple program makes use of all the essential functionalities and references. Okay, so you can create a ref, and when you create it, you have to give it an initial value. So you can't create a ref with nothing, although you can do that with singleton arrays. You just can't do it with this particular template. Okay, and then you have a void. So you're just going to run this, evaluate this void expression, which increases the integer assigned at ref. So if we have that, then we have this. Yep, terminated, and now x equals 5. Where is it terminated? So the first line creates a reference restoring an integer and initializes the value of 0. Then we're naming the reference intr. And note that you can't have this at the top level, so this is a global variable. It's a mutable global variable now. Well, global as far as these two expressions can see it. All right, note this style of reference creation cannot be separated from its initialization. You have to initialize it. The second line updates the reference with a new value. In general, given a reference of the type int, given a reference r of type ref of t for some t, the expression bang r means to fetch the value stored at r. Okay, so if x is a reference, then bang x says, okay, give me that reference. Not in this case though. In this case, we're actually assigning it. But over here, this right here is an expression that evaluates to the contents of the reference. All right, and however, r can also be used as a left value, which explains the x on the left side of this assignment operator. So there are functions and function templates for references in the file reference.stats. So this is part of the standard, the prelude that we're loading. Yeah, this is what it looks like. So we got ref takes a linear type and creates, I guess, WRT. This syntax right here tells you what effect a function has. So like if let's say you had a function factorial function, takes an int, turns an int. You can say, okay, this is actually a total function, so it's pure. And this right here says, I guess you could say what it's saying is that there are no effects because your effects will be listed here. So yeah, it's a pure function. So WRT, I don't know what that means, but I guess what it's saying is that it has the an effect of updating permanent storage. Ref make elt, which looks exactly the same. Make view pointers. This is a cast function. So if you have a view and an address, you can turn that into a reference for free. That's interesting. I did not know about that. Well, anyway, that's part of the prelude. So in particular, it is also possible to read and write to a reference using the function templates refget.elt and refset.elt. So the thing we just did with like bang r, it's calling this function. The thing to do with assigning it, it's calling this function. So references are often misused in practice, especially by beginners of functional programming who have some previous exposure to imperative languages. So you're looking around like, oh man, like how do I have global mutable variables, or how do I have mutable variables? And finally you find references, you're like, all right, here they are. I was looking around for the mutable variables in this language and I found them. This is it, and I'm going to use them for everything. So he says, don't do that. So this is a function that uses references to sum up the elements of a list. So instead of using like a tail recursive loop that has an accumulator that you just add things to, so now let's instead of having passing the so it checks I, and if I is less than n, then it does all this mutation otherwise, and then it calls itself. So there's no else here. It just does mutation and it recurs. Well, that works. That's one way to do it. This is a correct but poor implementation, and its style, though not the worst of its kind, is deplorable. As references are allocated in the heap, reading from and writing to a reference is much more time-consuming than reading or writing to a register. So yeah, if this were a tail recursive loop and you're adding to accumulator, like you're literally like it's one instruction, it's add, and it's an add instruction to a register, a value in a register. So that's about as efficient as you can get. But no, we're not doing that. Instead, we're writing to memory, which validates cache or whatever. It's going to be really. I should probably benchmark this in another video and show like this should be actually slower. Anyway, So every call to sum up creates 2 references in the heap and then leaves them there when it returns. So you also need a garbage collector now, or you're going to leak memory because these references, you can't clear references. So for here, it's fine. Like it's a global variable, it's persistent, and it's just going to persistently be there throughout the run of the program. That's fine. I don't care about that. But when you have references in a function like this, then you're creating them, and then you need to have a garbage collector now. Otherwise, they're not going to be cleared. So fortunately, ATS can have a garbage collector, but well, now that constrains you in other ways. So more importantly, in programming, making heavy use of references is often difficult to reason about. So it sucks. It's bad. Performance is bad, but the important thing is that it's a lot harder to follow. And also, another important thing is not only is that's the classical argument that people make. Oh yeah, it's much easier to reason about programs when they're in a functional style. But also, ATS has features that rely on things being in a functional style. So, for example, you can't have a termination metric for this loop anymore. So you can't statically prove that the loop terminates. But if you had a tail recursive loop, you actually could do that, and that could benefit you. So I consider references a dangerous feature in functional programming language. If you want your program to run without a GC, then you've got to avoid these in the body of a function. And also there are many other restrictions if you don't have a GC. If you find that you are in need of references to translate, in scare quotes, imperative programs into functional ones, it is most likely that you are lost and you have not learned the way. So you're doing it wrong. Here's an example of a counter. So this is sort of interesting. So a counter is a record type, and a record has 3 elements that are all closures. And then he has this function called new counter, and he creates closures that close over this reference. So even though this is a reference within a function, it's not necessarily just leaking, because if you keep this counter around, you've got it. So let's actually do this. So fun new counter. It takes void and returns. I guess that the type def is so you don't have to have like the mess in this answer. So type def counter. It is a reference record. Clarify one int. Okay. Int. So these are references to functions that are closures. So you're getting the value, you're incrementing the value, and we're setting the value. Well, it's a little awkward. I'll do it like that. All right, how's that work? Tag identifier count isn't recognized. Okay, so I wanted to call it counter, and then I copied that instead of remembering if I'd renamed it. So just call it count like we had this code expects. All right, that works just fine. So let's use it. So x dot get. I'll increment a few times, and then get it again. Hold on. Symbol print can't be evaluated. There's a bunch of stuff here, so let's look at it. Line 54. Okay, so print can't be found. There's no match for this overloaded print. So it doesn't know what kind of value this is. Oh, I'm trying to print void. That's always a mistake. All right, I got syntax errors, line 55. Oh. All right, so x is initially 0. If you increment it a few times, you print it out again. Now it's 3. So yeah, that is one way to get something like objects. No, this isn't a persistent object, but it could be. I think we used a... Well, there's another video where I go into that, but if we... You can't just say type vdef. You have to keep this type def and then create a data view type. Like counter equals... or counter vt. And then you just create the record within this data view type, and that's how you get a linear object. All right, so this is often referred to as state encapsulation in OOP, in object-oriented programming, because you have this reference, and you can't actually... Nobody can see the reference. Nobody can reach in and change the reference. The only accesses to this reference are through these closures. So we've reinvented object-oriented programming right there. It's a very easy thing to do when you have closures. All right. Now we're talking about arrays. So earlier it was said that a reference is just an array of size 1. Okay, well, the reverse is also true. An array of size n is just n references allocated consecutively. So those references can be called cells, and they are numbered from 0 to n1 inclusive. Given an array of size n, an integer is a valid index for this array if it's a natural number, between 0 and less than n. Otherwise, the integer is out of bounds of the array. So if you have, let's see, x, it's an array ref of like ints, and it's 2. You don't have to do this. I'm just doing this to be clear about the type that I want to do. So array ref. Counter's been recognized. Oh, I deleted the type def. Okay, well, never mind. We've already done all that. All right. So this is an array of 2 elements that are ints, and those elements are 1 and 2. And you can see if this is just 2 references to 2 different two references. You can say it that way as well. All right, and the indexes that are in bounds of this array are 0 and 1. Because those are the only numbers, the only integers that are between 0 and 2. These are the only integers that are within 0 and 2, like that. And anything else to be out of bounds. For an array named A, the expression A, and then in brackets, square brackets I, is how you fetch the content of the cell in A that's numbered I, if it's a valid index for I. Okay. This is all very similar to how arrays work in other languages so far. So just like that. And this is a compile time error. This is not a runtime error. There are some unsolved constraints. Please inspect the above reported error messages for information. So the unsolved constraint is we have a less than that's not satisfied, and we have a 2, and the 2 is not less than 2. That is true. 2 is definitely not less than 2. So this 2 right here is not less than this 2 right here. All right. And then we have assignment as well. I probably need to do this. No, it doesn't have that. Yeah, so I'm lying now. So yeah, well, we have an array. We're looking at a member of that array. We updated it. Now we're looking at it again. So just like you can do with references. So what happens when the index I and a brackets I is invalid? So it's out of bounds of the array. And we saw that just a moment ago. And he says that's referred to as out of bounds array subscription. And evaluating that will lead to a raised exception, where the exception is array subscript exception. But we didn't actually see that. We saw a compile time error instead. It's with constraints. That's because this is an array ref which has constraints on the array indexing operators used for it. And this were just a let's get rid of this. RPCs, or was it R size ref? Okay, that also works. But now look at this. Uncoded, so it does the same thing in the whole. I added to the program, the behavior of the program. So it did all that. It printed out the member of the array. It updated it and printed that out again. And now uncaught exception at runtime, array subscript exception. So yeah, that's what you do if you have R size refs, which are these are checked arrays. So array ref, I like these better. One simple and reliable way to tell whether an integer is a valid index is to compare it with the size of the array at runtime. This is what we just did with the checked arrays. All right, so those are called R-size arrays. From now he's going to talk about arrays as just R-size ref. So all the discussion in this chapter about arrays are referring to not array refs like I have here, but the R-size ref arrays, which are just they're arrays that know their size at runtime, and all operations against them were checked against the size. And this is where they're okay. So after we say we're going to talk about R-size ref only, is well, there's more stuff at array ref. Yeah, but that's different stuff. So here are functions. We can create an R-size ref of elements. So whereas I have like a literal sort of, this is sort of an array, something like an array literal, where I'm creating an array of these elements. But you can also just say, give me like 10,000. So give me y. I want R-size ref, make elt. I want 10,000 of them, and I want them to be. I want all 10,000 of them to be 0. Usually you want zeros, don't you? Mismatch of static terms. So the needed term is this is an int or an int 1000. What it's not is a size t, so IT size. That's fine. And then we have the getEltAt and the setEltAt, which are overloaded into we're using that the bracket syntax for those. So as for programming with arrays that carry no size information, it's a topic to be discovered after dependent types. So the array ref thing I'm talking about here, where there's no size information, therefore you can't have runtime checking. That's really we need to do. It's going to take us a while to get there. So like in C, there are many types of integer values in ATS. The type size t is essentially for 64-bit integers on 64-bit platforms that are unsized. So there can functions that convert between int and the type size t. So g is 0 int to uint int size, and g is 0 uint to int size and t. So this takes an argument of type size and returns an int. It's encoded into the name of the function. But there are probably abbreviations for those. Like I used I2 size. So given the type t and two values, ASZ and init, the types, he's talking about these functions above. So yeah, you can create arrays like that. You can get the size of arrays like that. And also there's an overloaded dot size function you can call. So. Hold on. Okay, so I have a type where it's expecting a view type. What? Where is that? Line 37. Mismatch of sorts and unification. The dynamic expression cannot be assigned the type R size ref linear. That was a linear string. Hold on. Go away. R size ref. Okay, so this is fine. If I try and print out size, that's no longer fine. What if I just do this instead? R size ref get size. No, it doesn't like this anymore. Mismatch of sorts and unification. A sort of variable is type. A sort of solution is view type. What do you mean by solution? R size ref get size. But you're a star. Okay, that's definitely it. That's the first error here. It's expecting a function? No. I'm not sure what the problem is here. Let's see if we have an example of it. So this is an insertion sort implemented for our size refs. So, well, this, yeah, we're not actually, okay. Oh! No, that's not it. What is A? Where is A defined? Okay. I don't see A actually defined. There's no parameter called A. So we have insertion sort. Oh, right way up here. Our size ref of A. Okay, so we have an array of some int, and it's a sized checked array. Hold on, is that why? What was the actual? What was it called again? So our size make alt. Okay, so it's a template. I want to make an array of ints. Thank you. Now it works. And that works. Okay, so very important to know if you're dealing with a template or not. All right, then we have another example working with permutations of arrays. I'm going to skip that. And now we're to matrices. We saw the where expression here, which I've been talking about that continuously because I really like wheres as opposed to like let expressions or let declarations or no, the let expressions. Okay, so matrices. So a matrix in ATS is just a two-dimensional array, but it's represented by a one-dimensional array, and the representation is of row major style. So not column major style, which is the row major style is the usual one you expect unless you're trying to be optimal for some kinds of operations. It's like each row is laid out by itself in memory. So if you have a matrix of 5, so if you have this, a 2x4 matrix, then in memory what you find is 1, 2, 3, 4, and then 5, 6, 7, 8, rather than 1, 5, 2, 6, 3, 7, 4, 8. And that's just that's not something fundamental to the language. It's just how the ATS prelude happens to implement these matrix functions. So yeah, you can create a matrix of 2 different sizes, and you give it an initial element. Basically just like arrays. All right, this is all pretty straightforward. So it's assumed to be square. And it's another example of Monte Carlo methods on estimating the constant pi. Let's go to simple input and output. So handling I/O in ATS properly requires the availability of both dependent types and linear types. How does I/O require dependent types? Anyways, he presents a means of allowing a program to access. So this is very basic I/O. Apparently, they're going to have more I/O, and that more I/O is going to involve dependent types and linear types. We're not there yet. So, okay, yeah, obviously, file handle. So, if you yeah, so if you like, if I were to use if I were to use like the basic like file operations here, then I'll be creating like linear objects and working with them. So, but since he hasn't talked about linear objects yet, we're not gonna work with like the normal file operations yet. And I say normal, but if you load the ML prelude, then you get garbage collected files that aren't linear values. So anyway, the type for file handles in ATS is file ref, file in all caps ref. So, and the names of the normal file refs are syn underbar ref, stdout underbar ref, standard error underbar ref. And that's all defined in file bas.stats, which you can look at. So we have an exceptional file ref open. So it tries to open a file, and if it fails, there's some kind of exception. One thing it does, it doesn't say what kind of effect it is. So even though we're talking about effects, it's not telling us how you talk about effects in the programming language. Oh, that failed. Oh, that worked. Okay. File ref open. Oh, it doesn't have it there either. It doesn't say that this has some kind of effect. We just have to know that. But there are ways in the language to say that. So, Okay, so the file ref open exception and the file ref close functions, they just throw an exception if there's an error. The following one, like this right here, file ref open opt, this returns an optional type. Then we have modes. Appending is always the important one. If you don't have O-append, then you basically have to throw away your whole IO abstraction and just use whatever C has, unless you want to be particularly inefficient with like logs. So you've got all that. One thing to note is you don't have strings, like it's not double quote R. You have these specific types. And this is how I imagine you'd handle options, like a usual, like there are lots of options in C interfaces, like man to open. So the underlying syscall has all these options. And O-append, async, close on exec. And these are constants that you OR together to get, a constant, basically a bit array that says all the options you want. But in ATS, you have, in this case, an exhaustive list of options that just have all the methods you want. So you can have read, or you can have read and write. You can have write, or you can have write with truncation. Creating a new one. We're both reading and writing. This is like read and like this is file mode RR, except it'll create a zero file for you. So yeah, this is you can learn this and use this, but I'd rather have something a little bit more similar to the open syscall. So, but we'll talk. That's not going to be something we talk about when in this video series. Okay. So as an example, the following short program opens a file handle, puts a string hello world, and then closes it. Let's do that. Okay. So we're creating we're calling it file, or calling it out. Fprintln, using the macro instead. Hello world. So that happened, and hello text now exists. Let's make it appending now. So run if you would. Okay. So there you go. We're opening a file and we're writing to it, and let's do this. We're opening the file. This is the write. Where is the Alright, open hello, and the options we're passing are we're write only, we're creating if it doesn't exist, and we're appending. So any kind of writes to this file that we open, they're going to go to the end and it'll be atomic. Alright. So that's straightforward, and one thing to point out is that we're closing it here. What if we don't close it? It doesn't complain. Okay. What if we try and close it multiple times? We get a really terrible error. What? Whoa, what is this? I believe this is a... My kernel is freaking out? So this isn't a bug in ATS. This is like a console message. The Linux kernel is upset by what I'm trying to do here. That's odd. Anyway, the point is, out is not a linear value, so you don't have to close it. You don't have to terminate it, which is what close you normally want to do. I'm disturbed by that, but let's move on. So after executing the program, we have a file named hello.txt, and it has the contents of hello world in it. So yeah, there's a bunch of stuff like that, obviously. Another common IO function is this one. This is a little different. Fileref get line string. So it's reading a line, which is a complex high-level operation. It's like, well, how long is the line really? You read the line however long it is, and you get a store pointer 1, which is a non-null string, a linear string. So it's a linear string, and it's not null. This does not return null. It returns something that definitely isn't null. So here's a function that says as long as standard input isn't null, as long as it's not EOF, as long as we haven't run out of standard input, let's keep reading lines and printing out them. And then now we have to free them because this is a store pointer, so it's a linear, so we have to free them. And then it ends. So let's do this. This is just like a... This is cat, basically. Include, share, ATS preload, stload, prelude, stload. What main? We're going to open a file instead. I'll do it like this. This is like println, like println, but to standard error. So you don't have to do. You could use like fprintln like that, and then std error ref. But it's a very common thing to want to do. So it's this as well. Your cats should always be fun cats. So we're running off the right side of the string, the right side of the screen, but that's fine. That's how I'm going to do it. All right. Okay, so if we're not at the EOF, let's not actually do that. If we're not at EOF, then get a line, Fileref get line string from the file we have open, and then print it out. I believe free is fine. You don't have to actually say stir pointer free. Okay, that's overloaded. And yeah. So if we're not at UF, then get a line, print it out, free it, and then loop and continue. How does that work? Arity message, arity mismatch, more arguments than are expected. Line 5. Line 5. Fileref open exn. Oh, yeah, we need to pass it to file mode. Alright, mismatch static terms. We have a void, but we're returning. Oh, no. We have, we have a void, but what it wants is some kind of int. Sorry, actually, what line was that? That was line 21. Stop that. 21. Okay. This should be void. Cat's void. This expression's void. So what's the problem? That's also void. Everything's void here. Dynamic expression cannot be assigned the type G0 int. Line 21, offset 9. 21. 21. 9. So why does it want this to be an int? Oh, because this is main. So main has to return the return code. But I want main 0, so I just want it to always return 0. And this thing right here, fileref get line string. Since that is like a complex operation, it's actually implemented in the ATS runtime. So it doesn't just synthesize that. You have to actually. It's actually implemented. Hold on. My reference. Make. Oh, I see. I have like special handling for in files, like in number. So let's call it cat lc.dats and remove cat underbar. All right. And it still wants the ATS libs. Okay, never mind. Count lc.dats, cat gc.dats. I think I add ATS lib on that. If I don't, then my make file is incomplete. Well, it already has, but yeah, there we go. All right, cat gc, garbage collected, and let's do hello.text. That didn't go well. Yeah, that one's gone. Okay, hello world. That's good so far. Now it continues. It's continuing. Cats.dats no longer available. Okay, it's called cat gc.dats now. So what is the problem? What happened here? So file open exception. So it opened fine. I said, okay. Oh, I'm checking standard input. Yeah. So as long as standard input isn't at EOF, then just continue trying to read from this file. In fact, what I was getting is empty lines from this. So it'll keep giving me lines after EOF, but the line will always be empty. So now, how about file instead? This is not an error that an ATS can protect you from, unfortunately. Add 100. Okay, yeah. So it prints out everything, and then it prints out an empty string, which is it's a little bit unfortunate. Right? Like the empty string is not part of the file, so this isn't really good implementation of cat. So we get EOF after we try reading a line. So what I should say is that if a line is empty, then don't do it. Because if a line is empty, then it's really not in the file unless the file is empty itself. In which case, I don't want to print on nothing, so I still don't want to do that. Because this print line... Oh, no, that's right. This function is also, it's removing the line terminator. So that's why print line is not adding line terminators. Do it like that, then catchy C. Now it's all on one line, even though there are new lines in the file itself. Okay, so you can legitimately have empty lines. Let's try like this. So only print it out. Hold on. If it's not, then we want to do all of this actually. Else, we only want to free the line, but we still have to free the line. Since this is a linear, this would ATS would have actually caught that error. All right, can't you see? Hello. All right, that's good. That's good. So we always get a line, but after we try and get a line, we say, hey, did we run out of file? Okay, if we did run out of file, then just free the line we got. That's a better cat. All right, and that is the end of the chapter. That's the end of the video as well.